Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we had talked about the ordinary least square estimation, and now in this lecture we are going to learn some results related to the ordinary least square estimator of the regression parameter in the multiple linear regression model or multiple linear model, and we will try to associate the ordinary least square estimator with the concept of estimability of a linear parametric function. And after that we will also learn that how one can estimate the same parameter beta through the maximum likelihood estimation. So, let us begin our lecture, and first we try to have a quick review of what we had done in the earlier lecture. So, the model that we are going to consider here is like as follows: let y1, y2, yn be a sequence of n independent random variables associated with a response variable y. Then we can write these random variables. I is equal to summation j goes from 1 to p beta j xij plus epsilon I, and I goes from 1 to n, j goes from here 1 to p. So, we have p independent variables which are indicated by x1, x2, xp, and beta 1, beta 2, beta p, they are the unknown parameters. They are associated with these independent variables x1, x2, xp, and epsilon i's are the IID random error component, and small xij's, they are going to represent the known values of this independent variable. And we also assume that expected value of epsilon I equal to 0, variance of epsilon I equal to sigma I square, and covariance between epsilon I and epsilon j is equal to 0. That means all epsilon I, epsilon j are IIDs having a mean 0 and variance sigma I square. Then after this we have found the ordinary least square estimator of beta from this model y equal to x beta plus epsilon, and this estimator was obtained as beta hat is equal to x transpose x whole inverse x transpose y, and this least square estimator is the best linear unbiased estimator of beta in the sense that it has got a minimum variance in the class of linear and unbiased estimators, right. So, now in case if you try to consider the estimation of a linear parametric function, and if you try to associate this least square estimator to estimate the linear parametric function, then how to get it done and what are the results related to this, now we are going to talk about them. So, suppose if the linear parametric function is given by L transpose beta. So, where here this capital L is has the elements L1, L2, Lp that are some scalars known values, and this capital L is a non-null vector, that means this L1, L2, Lp they are not equal to 0. And suppose we want to find out the least square estimate of L transpose beta, that is the linear parametric function. So, in that case we are simply going to replace this unknown beta by the estimator beta hat, that is the least square estimator of beta, and then the estimator of L transpose beta linear parametric function becomes here L transpose beta hat. Now, natural question arises here that what are the conditions under which a linear parametric function's L transpose beta admits a unique least square estimate in the general case. Right, how are you going to say that you have given the estimator as a L transpose beta hat, where beta hat is the least square estimator of beta? How you can ensure that this is going to give you a unique estimator? So, in order to explore this thing, we need the concept of estimable function, and using this concept we can find such conditions. So, the first question comes, what is an estimable function? So, in case if you try to consider here a linear parametric function, say lambda transpose beta, and where this lambda is a vector of some known values, and beta is your parameter vector of beta 1, beta 2, beta p, then this linear parametric function lambda transpose beta is said to be an estimable parametric function, or it is called as estimable if there exists a linear function L transpose y, and this linear function is of the variable y, and this function has been defined such that expected value of L transpose y is equal to lambda transpose beta. So, that means in case if you can find out an unbiased estimator of lambda transpose beta in the form of a linear function L transpose y, then this function is said to be estimable, and here this beta belongs to the RP. Now, we have to understand one thing, that not all parametric functions are estimable. So, now the next question comes, what are the parametric function that can be called as estimable, right, or what are the conditions which are needed for a parametric function to be estimable. So, now we are going to use some results which are going to help us in understanding these concepts. So, these results I have given in the form of here theorem. So, and I have given here these theorems are number, and these theorems are going to be used in the further lectures also, when we will try to construct the statistics for conducting the analysis of variance test. So, it is important for us to just remember these theorems, and if you have any problem in the further lecture, you can always come back to the earlier lecture or to the slides and can see what was theorem 1 or say theorem 2, right. So, the first theorem is a linear parametric function L transpose beta admits a unique least square estimate if and only if L transpose beta is estimable. This is my theorem 1, right. And theorem 2 here is this is also called as Gauss-Markov theorem, and this theorem says that if the linear parametric function L transpose beta is estimable, that is the first condition, then the linear estimator L transpose beta hat, right, beta hat is an estimator of beta, and this beta hat is a solution of this normal equation x transpose x beta hat is equal to x transpose y. Do you remember what was this thing? If you remember, this was your normal equation when you were trying to find out the ordinary least square estimator, right. So, now we are trying to say that beta hat is the solution of this normal equation x transpose x beta hat x transpose y, and this beta hat what you are going to obtain from this normal equation is going to be the best linear unbiased estimator of L transpose beta. Best linear unbiased estimator means that this estimator L transpose beta hat will have the minimum variance in the class of all linear and unbiased estimator of L transpose beta. This means here what? Suppose if I say, suppose I have here this linear parametric function L transpose beta, and suppose I want to estimate it. That means because beta here is unknown, so I need to find out the estimator for beta. Suppose if I say I have here, say here 3 estimators, say beta 1 hat, beta 2 hat and beta 3 hat, right. Suppose they are obtained by different process, different estimation procedures, and they have got a different form. So, now I am going to first find out that which of the estimator here is unbiased. Suppose beta 1 hat is unbiased and beta 2 hat is also unbiased and beta 3 is biased estimator of beta. Now, I try to ignore this biased estimator and I try to consider only these two unbiased estimator, but my problem is that which of the estimator beta 1 hat or beta 2 hat I should use to replace in the place of beta in L transpose beta. So, for that this theorem is informing us that out of this beta 1 hat and beta 2 hat, whichever estimator you are trying to obtain by solving the normal equation x transpose x beta hat is equal to x transpose y, that is beta hat is equal to x transpose x whole inverse x transpose y, and then if you try to replace here L beta by here L beta hat, then this is going to give you the minimum variance between say L transpose beta 1 hat and L transpose beta 2 hat, right. So, whichever is going to be here minimum, that is going to be the same as your here beta hat, which is least square estimator, right. So, this theorem is simply informing us that in case if you try to use the least square estimator to estimate the parameter vector beta in the linear model, and in case if you try to use this least square estimator to estimate the linear parametric function L transpose beta, then this will give you the minimum variance unbiased estimator of L prime beta, right. So, I can now say in very simple words, in case if you have got a linear parametric function and if you want to estimate it, simply try to use the ordinary least square estimator of the parameter vector, and then the estimator that you are going to be used is going to be your ordinary least square estimator, and if you try to do so, you will get an estimator which will be having the minimum variance in the class of linear and unbiased estimator of that linear parametric function. Okay, so, now we have one more result here in the form of theorem number 3, and this result is related to the case when we have more than one linear parametric functions, and this is talking about their estimability, right. So, suppose we have here k linear parametric functions which are indicated by here phi 1, phi 2, phi k, and it is given like here phi I here is given by say L I prime beta, right, and I goes from here 1 to k. So, in case if I assume that all this phi 1, phi 2, phi k they are estimable, then any linear combination of phi 1, phi 2, phi k will also be estimable. So, that means the advantage of this theorem is that whenever we are trying to consider more than one linear parametric function that are estimable, and if you want to find out a function of those linear parametric function and that function has to be also estimable, then simply try to take the linear combination of those estimable linear parametric function, that is all. Okay. So, now after this we have here one very important result in the form of theorem 4, and here we are going to talk about that what type of linear parametric functions are going to be estimable. And this is a very simple condition, but very useful, and we are going to use it many times. So, this theorem number 4 says that all linear parametric functions in the parameter vector beta, they are estimable if and only if x has a full rank, that is all. If you try to see what was your here x, this was the matrix of observations on independent covariance, right. And you had this independent variable x1, x2, xp, and then the order of x was n cross p, where you are trying to obtain an observation on each of this independent variable. So, if you try to see, this condition is very simple. So, you simply has to assume that rank of x has got a full rank, that is all. And what really happens if x is not having a full rank? In case x is not of the full rank matrix, then some linear parametric function do not admit the unbiased linear estimators, and nothing can be inferred about them, right. And that you will see that when we are trying to conduct the test of hypothesis, whenever we are trying to construct the statistics, you will see that when x is not of the full rank, then these estimators are not really going to give us a clear inference, but there will be some problems, some issues that we will try to see when we come to those lectures. And the linear parametric functions which are not estimable, they are called as confounded. This definition, this word confounded, is very useful when we will be dealing with the factorial experiments. And I have one request to you all, that in this lecture I have given you the formal definition of confounding or confounded effects, that the linear parametric function which are not estimable, they are said to be confounded. This definition you have to keep in your mind, and this definition is going to be used when we are going to consider the factorial experiments that will come towards the end of the course. But at that time I will use it, and then I will request you all to recall this definition. Right. Now, after this we have one more theorem, Theorem 5, and this theorem is about two estimable linear parametric function based on the ordinary least square estimator, and it is giving us a result about their variances and covariances. So, suppose we have here a linear parametric function, say L transpose beta, and for which we have two different linear parametric functions that are estimable, and they are going to be indicated by here, say here L1 prime beta and say L2 prime beta. Both are estimable parametric function. And suppose this beta is going to be estimated by ordinary least square estimator, that is x transpose x whole inverse x transpose y. And you try to replace this beta by here this beta hat. Then L1 transpose beta hat and L2 transpose beta hat are going to estimate L1 transpose beta and L2 transpose beta respectively, and they are their least square estimators. Then in case if you try to find out the variance of these estimators. So, for example, I have considered here the variance of L1 transpose beta hat. This is simply going to be sigma square L1 transpose x whole inverse into L1. And similarly, if you try to find out the variance of L2 transpose beta hat, that is going to be sigma square L2 transpose x whole inverse L2. And in case if you try to find out the covariance between L1 transpose beta hat and L2 transpose beta hat, this is obtained as sigma square into L1 transpose x whole inverse L2. And here we are using the term x transpose x whole inverse. So, we have to assume that x is a full rank matrix, so that this inverse x transpose x whole inverse exists. And as we had discussed earlier, that in case if x is not a full rank matrix, then x transpose x inverse will not be unique, and in that case we can use the generalized inverse of x transpose x. But as we said earlier, as we decided that unless until specified we are not going to use it, but we are going to assume that X is a full rank matrix. But remember one thing, that whatever results I am trying to give you here, where I am assuming that X is a full rank matrix, and so X transpose X whole inverse can be found in a unique way. But in case if you are using the generalized inverse, then also these results have been given and they are well defined, but we are not considering here. If you wish, you can look into the books of linear inference, and then from there you can find it out. Right. So, now before I try to give you another result, let me try to tell you here one thing more. Whatever theorems I have done here, theorem 1, 2, 3, 4, 5, here you can see here that I have given you here only the statements, but definitely these theorems have got a mathematical proof also. But surely these proofs are available in the books of linear estimation, and I believe that you already have done these results and you know about them. That is why I am simply giving you here the results correctly, that we are going to use it. But in case if you have any confusion or you have not done it, my simple request is that you please try to look into the books of linear estimation, and there you will find out all the mathematical proofs. Right. Now, I take up another issue. I try to consider here the estimation of sigma square. Well, sigma square is the parameter. So, sigma square can also be estimated by different estimation procedures. So, here you will see that in this case of linear model y equal to x beta plus epsilon, we are going to estimate the parameters beta and sigma square, and we are going to use here two approaches. One here is least squares approach, and second here is maximum likelihood estimation. So, up to now we have considered the least square estimation of the parameter beta. Now, we will consider the least square estimation of the parameter sigma square, and after that we will try to consider the maximum likelihood estimation of beta and sigma square. Those who have an idea about the maximum likelihood estimation, they know that we are going to write down the likelihood function, and we are going to differentiate the likelihood function with respect to the parameters, and we are going to solve the normal equation. But in this case, you can see when we are trying to use the principle of least square to estimate beta and sigma square, in this case we have obtained the estimator of beta by minimizing the sum of square due to random errors, and we have formal procedures through which we have obtained the estimator beta hat is equal to x transpose x whole inverse x transpose y. But when we are trying to estimate the parameter sigma square, there is no such formal procedure that you write the sum of square due to error or try to differentiate it. That is not possible, because if you try to see your sum of squares due to error that you had indicated by the quantity s square, summation I goes from 1 to n epsilon I square, this was written as say epsilon transpose epsilon, and this we had written as y minus x beta hat transpose into y minus x beta. This was only a function of beta, and there is no sigma square here. So, that is why if you want to differentiate s square to obtain the estimator of sigma square, this is simply not possible, because this function does not involve sigma square. So, that is why we have to opt here another approach, where we try to start with a possible estimator of sigma square, and then we try to take its expectation, and then we try to convert it into an unbiased estimator. So, that is the approach, but whatever is the approach after solving this, we are going to have these here following steps, right. So, we try to consider this form 1 upon n minus p into y minus x beta hat transpose into y minus x beta hat as a possible estimator of sigma square, where this beta hat is given by x transpose x whole inverse x transpose y, and this quantity I am going to indicate here as a sigma square hat. Now, in case if you try to substitute here beta hat is equal to say x transpose x whole inverse x transpose y here and here both, then you will get here this thing y minus x into x transpose x whole inverse x transpose y, and this quantity will have the whole transpose on the whole vector and then multiplied by this here y is coming from here minus x, x is coming from here, and then here this is beta hat x transpose x whole inverse x transpose y, right. And now you try to take out this y outside the brackets. So, I can write down here as say here like this. I try to write down here y transpose here and I try to write down here y here, and then the quantity inside the two brackets is simply I minus x x transpose x whole inverse into x transpose and I minus x x transpose x whole inverse x transpose. And in case if you try to multiply it, you can see here this is I minus x x transpose x whole inverse x transpose minus x x transpose x whole inverse x transpose plus x into x transpose x whole inverse x transpose into x transpose x whole inverse x transpose. So, now you can see here that this is here x transpose x and this is here x transpose x whole inverse. So, this will become here I, right. So, now we get here I minus here x x transpose x whole inverse x transpose minus x x transpose x whole inverse into x transpose plus here x x transpose x whole inverse and this here x transpose. So, you can see here this and this they get cancel out and we have here only I minus x x transpose x whole inverse x transpose. So, you can see here this is written here. Now, can you identify here one thing, that you are trying to multiply this matrix here by the same matrix here and this is coming out to be the same matrix here I minus x x transpose x whole inverse x transpose. So, this matrix I minus x into x transpose x whole inverse x transpose is an idempotent matrix, right, and this is called in the literature by different name, projection matrix, hat matrix, etc. So, we are just giving it a name as hat matrix. So, you can see here this sigma square hat comes out to be 1 upon n minus p y transpose I minus x x transpose x whole inverse x transpose into y. So, do not you think that this is looking like as an as a quadratic form like as y transpose a y, where a here is your entire this matrix, right. So, now we have to actually see whether this expected value of sigma hat square is equal to sigma square or not. So, and in order to see it, we needs to first know what is the trace of this hat matrix. So, first we try to find out here the trace of this hat matrix I minus x x transpose x whole inverse x transpose. So, you can see here that I can bring this trace operator inside the bracket. So, this becomes here trace of I into trace of this quantity x x transpose x whole inverse x transpose. Now, I try to use here a result trace of A B is equal to trace of B A. So, what I am going to do here is the following, that I am going to choose here A is equal to say here x into x transpose x whole inverse, and B I am going to use here as say here X transpose. So, you can see here I can write down here B A is equal to X transpose X into X transpose X whole inverse. So, this is going to be here I, identity matrix. Now, here I would like to play very safe. Means if you try to see here what is here this I, this is identity matrix, but I will try to write down here the order of this matrix, order of this identity matrix. Why? Because you can see here we have here one more identity matrix, this here I, and we have to find out here trace of I, and here also we have here I. So, now if you try to see what will be the order of this identity matrix, you can see here X has a order n cross P. So, this quantity here X transpose X into X transpose X whole inverse, in this quantity X transpose X will have a order P cross P. So, this X transpose X into X transpose X whole inverse, which is actually here identity matrix of order P, right. So, I can write down here this is of order P, and similarly if you try to write down here the order of this matrix I, and what is the order here? You can see here the order of this matrix here is like this. X has a order n cross P, X transpose X has an order say P cross P, and X transpose has an order P cross N. So, this whole product is going to have an order n by n. So, this matrix I has to be of order n, right. So, now if you try to see, if you try to simplify this thing, you can write down here trace of I is going to be here n, because you are trying to find out the trace of an identity matrix of order n. And for this trace here, this is here the trace of an identity matrix of order P. So, when you are trying to write down here a matrix of order n in which all the diagonal elements are going to be 1 and all off diagonal elements are going to be 0, then the trace is defined to be the sum of all the diagonal elements, that means 1 plus 1 plus 1 n times. So, this is going to be here n. So, this is how we try to find out the trace. So, now this becomes here trace of I p is going to be here simply p. So, this trace of this hat matrix comes out to be here n minus p. Now, in case if you try to use the result about the quadratic form, that expected value of y transpose A y is equal to trace of A into this sigma, where this covariance matrix of y is here sigma, right. So, in this case what will happen, because you are assuming in the case of y equal to x beta plus epsilon that the covariance matrix of here y, this is sigma square I. So, right. So, in case if I now try to take the expectation of this quantity, so this will come out to be expected value of sigma square hat is equal to sigma square into this trace of A here is obtained here like this trace of hat matrix, which is here n minus p, and in the denominator we have here n minus p. So, this n minus p and n minus p, they will get cancel out, and we get here expected value of sigma hat square is equal to sigma square. So, now we have proved that sigma hat square is an unbiased estimator of sigma square, where this sigma square hat is based on the least square estimation. Why? Because you have used here the least square estimator beta hat that you can see here for forming a possible estimator of sigma square, right. So, now you can see we have done the least square estimation of both the parameters beta vector and sigma square. Now, one thing you have to keep in mind that when we do the estimation in the least square method, then we do not need any assumption about the distribution of the random variable either y or say epsilon. But when we try to do the maximum likelihood estimation, then you know that first we have to write down the likelihood function and then we have to maximize it. So, definitely when you want to write down the likelihood function is defined as a joint probability quantitative function of all the random variables that are involved. So, definitely you need to know what is the form of the probability density function or probability mass function, whatever is the case, right. So, now we consider here the maximum likelihood estimation of beta and sigma square, and yeah, means I say beta and sigma square, that means beta is a vector, parameter vector, and sigma square is a scalar, right. So, in this case we need the distributional assumption right from the beginning, right. So, we assume here that y1, y2, yn they are independently and identically distributed, that means IID, and they follow a normal distribution with mean, which is here expected value of yi is equal to summation j goes from 1 to p beta j x I j, and variance, which is variance of yi equal to sigma square for all I goes from 1 to n. Now, you know that if you can recall that the PDF of this normal distribution is given by 1 upon sigma root 2 pi exponential of minus 1 over 2 x minus mu upon sigma whole square, right, and we say that this is my here normal mu sigma square, right, the parameters mu and sigma square, where mu is the mean and sigma square is the variance. So, now we are trying to write down the likelihood functions. So, we have to write down the joint probability density function, and because we are assuming that they are identically and independently distributed. So, I can express them in the form of random vectors or the vectors and matrix notations, right. So, the likelihood function of this y1, y2, yn is obtained here as say 1 upon 2 pi raised to the power of n by 2 sigma square raised to the power of n by 2 exponential of minus 1 over 2 sigma square y minus x beta hat transpose into y minus x beta. Why? Because if you remember, you had the model y equal to x beta plus epsilon, and you have assumed that expected value of epsilon is equal to 0 and variance of or the covariance matrix of epsilon is sigma square I, that means the variance of all the epsilon i's is sigma square, that in this case expected value of y is going to be here x beta. So, that is equivalent to your here mu, and variance of here y, this is going to be sigma square for all I, and the covariance, that is 0 because they are independent, right. So, this is how I have written here, where I am taking here this y to be here the vector of all the observation y1, y2, yn, right. So, now we want to find out the value of beta and sigma square by maximizing this likelihood function. So, we try to take here the log of this likelihood function, so that the differentiation will become easier. So, I try to take here the log of this likelihood function and then I try to differentiate it. So, when I try to differentiate it with respect to beta, we get here x transpose x beta equal to x transpose y, and sigma square is equal to 1 upon n y minus x beta transpose y minus x beta, right. So, you get here like this is equal to x transpose y, and sigma square is equal to 1 over n y minus x beta transpose y minus x beta, right. So, now means you cannot know the value. So, what we try to do here, that we try to pre-multiply on both the sides by x transpose x whole inverse in this normal equation, and we obtain here the value of beta to be here like this, beta to be here say x transpose x whole inverse x transpose y, and we try to indicate it by here b tilde. Right, I am not using here hat because we already have used the symbol hat to indicate the least square estimator of beta. And once I know the value of beta to be beta tilde, then this can be replaced here in the expression for sigma square. And now I can write down here an estimator of sigma square as sigma square tilde which is 1 upon n y minus x beta tilde transpose y minus x beta tilde. Right. One thing what you have to notice here, that when you are trying to differentiate this log of likelihood with respect to beta, what is the function that you are trying to minimize? If you try to see, this is this function here, you are trying to differentiate here y minus x beta transpose y minus x beta. Now, do you recall what was that function when you were trying to consider the ordinary least square estimation? This was same as your like epsilon transpose epsilon, and that is why you are trying to minimize this function, and that is why you are getting here a normal equation which is the same as the normal equation that you had obtained in the case of least square estimation. And if you try to see here, the least square estimator that you obtained earlier was beta hat is equal to x transpose x whole inverse x transpose y, and here also you are getting the maximum likelihood estimator of beta as x transpose x whole inverse x transpose y. Right. But in case if you try to look at this expression, the estimator of sigma square, this is different. In the case of least square estimation, the divisor was there, it was like n minus p, right. So, now in case if you try to assume here that from this normal equation which I solved here by pre-multiplying x transpose x whole inverse. So, you need to assume here that x has got a full rank matrix, and as I just showed you there, you can obtain the maximum likelihood estimator of beta as x transpose x whole inverse x transpose y, and maximum likelihood estimator of sigma square as 1 upon n y minus x beta tilde transpose y minus x beta tilde, right. And yeah, in case if you try to solve it here, we have solved this quantity here. If you try to see in this case, you have solved it, you can see here. So, if you try to solve it, I will not do it here again, but you will get here this expression 1 upon n into y transpose hat matrix I minus x into x transpose x whole inverse into x transpose into y, right. So, these are the maximum likelihood estimators of beta and sigma square. And now, since you have used here the maximum likelihood estimation, so you have tried to maximize the likelihood function using the principle of maxima minima. So, you also need to verify that the values of beta and sigma square that you have obtained here as beta tilde and sigma square tilde, they are really maximizing the likelihood function or not. So, for that I am not doing here, but I can inform you and you can check yourself that the second order differentiation condition can be checked, and they are satisfied for this beta tilde and sigma square tilde, and they are maximizing the likelihood function. So, this beta tilde and sigma square tilde, they are the maximum likelihood estimator of beta and sigma square respectively, right. So, now if you try to see the similarity between the least square estimate of beta and maximum likelihood estimator of beta, and the least square and maximum likelihood estimator of sigma square. What do you observe here? the maximum likelihood estimator and ordinary least square estimator of beta, they are the same, right, and both are the unbiased estimator of beta. That you can see, for example, if I try to take here this expected value of beta tilde, this is going to be expected value of x transpose x whole inverse x transpose y, and you can see here this will become here x transpose x whole inverse x transpose expected value of y, and expected value of y here is x beta. So, this x transpose x whole inverse into x transpose x becomes I, and this comes out to be here beta. So, both ordinary least square estimator and maximum likelihood estimator, they are the unbiased estimator of beta, right. But for the estimators of sigma square, the maximum likelihood estimator of sigma square indicated by sigma tilde square is not an unbiased estimator of sigma square, right. And you already had obtained earlier that sigma square hat was 1 over n minus p y minus x beta hat transpose y minus x beta hat, and you had proved that expected value of sigma hat square is equal to sigma square. So, in case if you want to find out the unbiased estimator, the divisor has to be here 1 upon n minus p, or the divisor will only be actually n minus p, and in this case expected value of sigma tilde square, this will not come out to be sigma square, because here the divisor here is n, that is you are trying to write down here 1 upon n, but the part in the numerator in both the cases, that is going to be the same, right. So, in case if you try to see here the expected value of sigma square tilde is n minus p upon n sigma square, which is not equal to sigma square, right. So, the maximum likelihood estimator is not an unbiased estimator of sigma square, but you have to remember one thing, the maximum likelihood estimators always give you an estimator which has got the lower variance. So, obviously, you who can see here you have the same quantity here y minus x beta hat transpose y minus x beta hat, and you are trying to divide it by here n or say n minus p. So, obviously, n is going to be greater than n minus p, and so when you are trying to divide this quantity y minus x beta hat transpose into y minus x beta hat by n, that is going to give you a smaller variance, right. So, now here the issue is the MLE is going to give us lower variance, but this is biased, and least square estimator of sigma square, that is going to give us an unbiased estimator, but it has got a higher variance than the MLE, right. Now, based on that based on these results, now we have some more results. So, the next result is in the form of a theorem 6. So, this is about the distribution of this quadratic form based on this y, right, although we have done it in the initial lectures, but just for the sake of quick revision and for the sake of clarity, that we are going to use this result in this format with this symbol. I am stating it here once again. So, let y be a vector of n random variables y 1, y 2, y n, and this is assumed to follow a multivariate normal distribution with the mean vector mu and covariance matrix sigma, that is going to be a positive definite covariance matrix. Then y transpose A y follows a non-central chi-square distribution with p degrees of freedom and non-centrality parameter mu transpose A mu, and this is indicated by like this chi-square, then p degrees of freedom and the non-centrality parameter mu transpose A mu, and this is going to follow this chi-square distribution if and only if sigma into A is an idempotent matrix of rank P. And you will see here that when you are trying to write down here y transpose into I minus x, x transpose x whole inverse x transpose into y, if this matrix here is A, that is your hat matrix, you had seen that this is going to be idempotent matrix, that you already have proved. right. And in this case you have assumed that covariance matrix of y here is sigma square I, right. So, you will see that we are going to use this result, and in this case we can see here that this matrix which is here idempotent, that is being used to construct this quadratic form of the form y transpose A y, then y transpose A y here, that is going to have a chi-square distribution with the degrees of freedom what, which is the rank of A, and the rank of A is going to be the same as trace of A, and the trace of A that you already have found to be n minus p, right. And you will see that we are going to use this result very frequently. Now, the theorem 7 is a result about the independence of two quadratic form which have got the chi-square distributions. So, let y be a vector of random variables y 1, y 2, y n, and this follows a multivariate normal distribution with mean vector mu and positive definite covariance matrix sigma. And suppose based on this y we have got here two quadratic forms with the matrix A 1 and A 2. So, this y transpose A 1 y, suppose this follows a chi-square distribution with the degrees of freedom P 1 and non-selectivity parameter mu transpose A 1 mu, and the next quadratic form y transpose A 2 y, this follows a chi-square distribution with the degrees of freedom P 2 and non-selectivity parameter mu transpose A 2 mu. Now, the main result is under what type of condition this y transpose A 1 y and y transpose A 2 y, they are going to be independently distributed. Now, here you have to be very careful when you try to use this result. You see, if I try to write down here two quadratic forms like this one, y transpose A y and z transpose A z. In this case, what is really happening? These two variables are different, but the matrix A in both the quadratic form is the same. And second option is here that I try to write down here two quadratic form, say y transpose A y and with the same variable y transpose A y, but this matrix A are now different, A 1 and A 2. So, we are going to consider here the variables of this type. So, in this case you can see here that y transpose A 1 y and y transpose A 2 y, they are independently distributed if the condition A 1 sigma A 2 is 0, that is null matrix, right. So, now we have here one more very important result, that is talking about the independence of a linear function and a quadratic form. And based on that, we have a very important result that is going to be extremely useful when we develop the distribution of the test of hypothesis while conducting the analysis of variance, right. So, this result is in the form of theorem 8, and here we assume that let y be a random vector of the random variables y 1, y 2, y n following a multivariate normal distribution with mean vector here mu and covariance matrix sigma square I, right. So, I am assuming that they are independent, right. Now, you have seen that if you try to consider an estimator of the linear parametric function L transpose beta as L transpose beta hat, then beta hat can be either OLSE, ordinary least square estimator, or say MLE, maximum likelihood estimator, because both have got the same form, right. So, I can write down here that the maximum likelihood estimator L transpose beta hat of estimable linear parametric function is independently distributed of sigma square hat, and this estimator of linear parametric function L transpose beta hat is following a normal distribution with mean L transpose beta and variance L transpose x whole inverse L, right. And sigma square hat divided by sigma square follows a chi-square distribution with n minus p degrees of freedom, where the rank of x is going to be equal to p, that is full column rank matrix. Right. So, we consider here beta hat is equal to x transpose x whole inverse x transpose y, and then expected value of L transpose beta hat becomes here L transpose into x transpose x whole inverse x transpose expected value of y, which is x beta. So, now if you try to see here that this is here x transpose x whole inverse and this is here x transpose x. So, this becomes here I, and we get here L transpose beta. So, you can see here this is an unbiased estimator. Now, in case if you want to find out the variance of this L transpose beta hat, this will become here L transpose variance of beta hat into L, and variance of beta hat is simply your here expected value of beta hat minus beta transpose into beta hat minus beta, and beta hat minus beta you can obtain here that x transpose x whole inverse x transpose y minus beta, and this is here x transpose x whole inverse x transpose y is x beta plus epsilon minus beta. So, you can see here this will become here x transpose x whole inverse x transpose x beta plus x transpose x whole inverse x transpose epsilon minus beta, and you can see here this is here x transpose x whole inverse, this is x transpose x. So, this becomes here I, and this beta and beta get cancel out, and then you have here x transpose x whole inverse x transpose epsilon. So, if you try to take here the expected value of here expected value of beta hat minus beta transpose into beta hat minus beta, this is going to be simply here expected value of here say epsilon, and then you have to write down this value here, and then you have to just solve it. You will get here so sigma square x transpose x whole inverse. Right. So, you can see here if you try to substitute this value here, this is sigma square into x transpose x whole inverse, you will get here sigma square into L transpose x whole inverse into L. Right. So, now you can see here that since this beta hat is a linear function of y, and because you can see here this is here y, and so this L transpose beta hat is also a linear function of beta hat. So, L transpose beta hat follows a normal distribution, because any linear combination of the normally distributed random variable is also normal. So, L transpose beta hat follows normal distribution with the mean L transpose beta and variance sigma square L transpose x whole inverse into L. Now, we try to prove the independence of this linear function and quadratic form. So, we try to indicate here this hat matrix by here capital A, and this matrix L transpose x whole inverse x transpose by here B. Right. So, you can write down here this L transpose beta hat here as L transpose x whole inverse x transpose y, which can be written here as a b into y, and this quantity and sigma square hat can be written as y minus x beta transpose into hat matrix I minus x transpose x whole inverse x transpose into y minus x beta. So, this I can write down here as a y transpose a y. So, now if you recall the theorem 6, we had rank of A is equal to n minus p. So, now I can write down here that n sigma square hat divided by sigma square will follow a chi-square distribution with n minus p degrees of freedom. Right. And in case if you want to prove the independence of these two, then you know that if you have a quadratic function y transpose a y and linear function b into y, then both are going to be linearly independent if b into a is a null matrix. So, if you try to use here this definition of a and b, and if you try to see here b into a, this comes out to be here a null matrix. So, using the theorem 7 earlier, we can write down here that y transpose a y and b y, they are independently distributed. So, you can see here now you can you have proved here all the results that this is normal, this is chi-square, and both are independently distributed. Right. Okay. So now we come to an end to this lecture, but in this lecture we have done very basic fundamental things, but they are the foundations when we are trying to develop the analysis of variance test, and there we are going to use these results to understand how are we going to derive and results. So I am sure that you have done it in the past, but these are the results that we are going to use. So it is very important for you that they should be in your mind and you are clear about them. So I would request you that you please try to revise these things, try to learn, and I will see you in the next lecture. Till then, goodbye.